Good morning, guys. Hope you're having a great day. And today we are going to solve a problem on Molier's chart. And hope you like it. And hope I teach you something today. So let's dive into the lesson and let's get started. So today's problem is on a Rankine cycle. So simple Rankine cycle works between pressures 28 bars and 0.06 bar. The initial condition of the steam being dry saturated. This is very important. Calculate the cycle efficiency, work ratio and specific steam consumption. So let us revise that our Rankine cycle normally looks something like this. Okay, this is the isentropic processes. This is the pump 1 2 3 4. This is the expansion, isentropic expansion in turbine. This is the condenser. This is the pump, isentropic compression, and this is the heat addition process. Now since over here it is given as dry saturated steam at initial condition, so this point comes over here. So how to draw that? So yeah, like this. So now this is point 1, this is point 2, this is point 3, point 4. Okay, so since we have cleared out in diagram, let's dive into the actual values. So now to find out the values of enthalpy, we have the Molier chart. I know many people just hate Molier chart, but trust me, Molier chart makes calculation much more easier. Just referring to the chart and knowing how to solve the problem, find the values, you can reduce your time in examination. So let's dive into a huge copy Molier chart and let's see the values. So the point 1 is at 28 bar. So over here 28 bar is approximately over here. These are all the values of pressure. So over here 28 comes over here. So that means that this is the enthalpy line over here. So this one enthalpy is 2800 kilojoules per kg is the value of enthalpy at point 1. So since it is an isentropic process at constant entropy, so the next point is exactly down over here. So now if we see this place, we have the second pressure line at 0.06 bar. So over here this is 0.05, as you can see over here. So this is 0.06. so follow this line exactly down over here. Okay, and here we have the 28 this point. So if we come down, so it means approximately over here. So I have taken 1870. Since we have point 1 and point 2 enthalpies over here, then we can refer to the steam tables and find the enthalpy at H3. So let us go. The H3 value is on the saturation dome over here. So this side, So this point we can find out on the steam tables for pressure, okay, not for temperature, because we know the pressure over here. So 0.06, okay, so for 0.06 we have HF over here as 151.5 kilojoules per kg, okay, and these are all the specifications at pressure 0.06 bar, okay. So we'll also keep in mind this volume, okay, specific volume at 0.06 bar. So let's write the given data what we have found out. So hope you can see H1 is equal to 2800 kilojoules per kg, H2 is equal to 1870 kilojoules per kg, and H3 we have found out from the steam tables as 151.5 kilojoules per kg, okay, and the specific volume we have is equal to 0.001006 meter cube per kg, okay. So once we have the enthalpy values from the Mollier chart, we can just dive into basic formulas, substitute and get what we need. Now in this case we need the efficiency, the work ratio and the specific steam consumption. Now all these things can be found out by simple formulas, just substitute. Hence we have to find out H4, I think so. So let's dive into those values. Now for cycle efficiency, the formula cycle is given as W of turbine minus W of pump. This is actually the net work divided by the heat input Q. So this we can write as in terms of enthalpies as H1 minus H2 minus H4 minus H3 divided by H1 minus H4. Now notice we have H1, H2, H3 over here, but we don't have H4. That is why I told you we need this specific volume, okay, to consider H4. Now to find out H4, we know that the pump work WP is equal to H4 minus H3. Also, since a pump has a constant volume and the pressure differs, so pump work can also be given as volume into integral of pressure. So this comes to V. For pump it is P4 minus P3, upper pressure minus the lower pressure. Since this is specific volume, we can equate this both to, since we have these pressures. Now you'll ask me, we have pressure at T1 at 0.1 and 0.2, but you see over here, let's dive into this. Is a constant pressure line, this is at 0.06 bar, and this pressure line, okay, is at 28 bar. So 0.1 and 0.4 are at same pressure, and 0.2 and 0.3 are at same pressure. So now let's equate this H4 minus H3 and this equation. So we have H4 minus H3 is equal to V P4 minus P3. So now the only unknown value is H4. Now substituting the values, we get H4 is equal to 0.001006. Now here the pressures are in kilopascals, so you know that bar, if you're converting bars to pascals, it is the bar into 10⁵ is equal to 1 pascal. Okay, so since here we have to write in kilopascals, it is 28 into 10⁵ minus 0.06 into 10⁵. Okay, this is when we are substituting this. Okay, then since this H3 comes over here, it becomes positive plus 151.5. so if you do the math on Calci, you get H4 to be equal to 154.3 kilojoules per kg. Now this is H4, and hence we can substitute in this equation to find efficiency. So now let's go ahead and do that. So cycle efficiency is given by 2800 minus 870 minus 154.3 minus 151.5 is 0.3. So this comes out approximately to 0.35, which is equal to 35%. So the cycle efficiency is 35%. Now the work ratio is just simple. It's the net work, it's the ratio of the net work and the turbine work. Just substitute the enthalpy values and you get the answer. So let's check out. It is quite equal to W net divided by W turbine. Okay, so this is in turn given by, you know, network H1 minus H2 minus H4 minus H3 divided by H1 minus H2. So substituting all the values again, that is 2800 minus 1870 minus 154.3 minus 15. Okay, 2800 minus 70. If you do the math, you will get that work ratio is equal to 0.997. Okay, your answers and my answers will vary, but that's not to worry. Okay, as long as you understood the idea, that's enough. So now heading back to our problem statement, we have to find out the specific steam consumption. Now specific steam consumption is similar to the steam rate. Now the steam rate is given by 1 by W net. Okay, now W net, you know, is just a subtraction of enthalpy, so this is given in terms of enthalpy is kilojoules per kg. So speed rate will be kg per kilojoules. Now the specific steam consumption is given by kg per kilowatt hour. Now you have to convert joules into kilowatt hour. Now what is a watt? A watt is joules per second. Okay, so joules is equal to watt second. Okay, so now this second you have to convert into hour. So what you'll do, you'll divide by 360. So joules W by 3600 will give you hour. So instead of joules, if you put 1 by 3600, you'll get watt hour. So joules, it's in denominator over here, 1 by 3600 will go up. So this in turn, the specific steam rate is given by 3600 divided by W net, kilojoules per kilowatt hour. So now W net, you know how to substitute. Now W net, this whole W net, so you substitute over here, H1 minus H2 minus H4 minus H3, 3600, and this I'm getting around 2927.3, and this is 3600. So if you do the math over here, you get the value of specific steam consumption to be equal to 3.88 kgs per kilowatt hour. So that's it in today's video. Hope you have learned something, and please share this video so that maximum people get to know about this problem. Very easy problem, not to take tension. Okay, and please solve it, and please hit the like button if I have explained it well and if you like the video. So thanks for watching once again. See you, bye bye. See you in the next video. Thanks for watching. Bye.